immer noch nicht, ja? Ich weiß auch nicht, das ist bei all den Dingern, da muss man immer 7-mal draufdrücken, bis okay, let's start right away. Let's have a look. Yeah, it's writing. Okay, that is the sheet of exercises we had started last week. We had seen the surface finishes, then we had derived the solution for a formula and a sketch for the limitation of the minimal pitch. And then we started with the individual steps of first surface mount technology process for the production of PCB assemblies. Then we have to describe the standard process to transfer a solder paste onto a printed circuit board, and also we make a sketch of it. And then what is important in surface mount technology is the temperature profile that we have in a SMT reflow oven. And also, there's a simple formula for soldering to determine the soldering temperature depending on what the melting behavior of the solder alloy is. Okay, so we have seen the surface finishes, and that is a sketch, first of all, of a device that is soldered onto a printed wiring board. And the paste is something that is important, but now here was the question, what are the individual steps of SMT? In the end, we are going to have a board that is something like that. That board can have devices, let's say bigger devices on one side. Like, for instance, we have ball grid arrays here. We could have such SO devices. And what do we have on the other side? So typically we have resistors or capacitors. That are soldered in this way. So the small ones on one side, the bigger ones on the other side. And what are the process steps to end up with this here? So how do we start? Yeah. Okay. So we print a paste, and that is a stencil printing process. What is next? What did you say? Pick and place, yeah? The devices. What then? Yes. And what do we do for, what do we do when we want to have double-sided? Okay, so we flip the board, and then what we can do is, if we have a SMT process, we go in here again. Yeah, so and what when we have a wave soldering process, what do we have to do then? Yeah. So yes, so we have that auxiliary adhesive. Then we pick and place devices. Then we harden the adhesive. And then after hardening of the adhesive, we again flip the board. What do we do then? I know the reflow was the second round here. Yeah. So yes, reflow. When we have SMT reflow, we repeat it. Just sorry. No, we just have attached the devices, so they have a, let's say, a little glue here. That fixes them. But then we put on the flux. Yeah, in some cases we do it before we flip the board. Sometimes we do it afterwards. That can be spray or foam. And then what kind of soldering process do we have then? We have wave soldering. The last step is, the last two steps is number 11, optional clean. So last week I was visiting a company. They are doing much for aerospace. So they always clean after soldering. So in normal automotive applications and household applications, you do not clean normally. And what comes after that, that was not in the lecture notes, but we inspect and rework. Inspection means, in the easiest case, there is a person looking at the boards and whether they, especially the solder joints, look good or not. And of course, that only works for solder joints that are visible. If it is invisible solder joints, we do X-ray analysis. Or we can also do some electrical tests sometimes. And then rework means local heating and putting on a new device. Presently, the availability of devices is just bad in the market. And so sometimes people take boards, for instance, prototype boards, and they solder out the devices only if they are new and put them on other boards. So that's presently not such a good situations. And so also some devices, especially those that are hardly available, have become really important. I heard of in some instances of a factor of 50 increase in costs for one device. Okay, so that was the steps of the surface mount technology process. But the next question is, yeah, what was it? Transfer solder and paste, and that is number 29. And how is that accomplished? What do we need for that? So first we have the board. These are the copper conductors. We have a solder resist here. Yeah. What else do we need? We need an E here. So how do we get the solder paste? And where do we want to have it? Okay. So we have this solder paste. It must be deposited like that. And what we need is, yes, yeah. Until here we are finished. And we need a mask. So here is our mask. And then we need a, yeah. We need a squeegee. Squeegee is like a piece of rubber. That is pressed here. And the solder paste must come here. So that's a big blob of solder paste. And here is the printed solder paste. So the squeegee is moved in this direction. Question is, did I miss something? Probably not. Now there are the questions. You called it that grid. How do we call it? It's a printing mask or a printing stencil. How do we get it? So we need it. Where do we get it? Yeah, who does that? You can cut it with a knife, but that's not convenient. So we make a CAD layout. In fact, it's not a special layout, but it's a layout derived from printing wiring board design. That can be made by an automatic machinery. Of course, we can also design it manually. So we have a CAD layout. And what's the important process to get such a sheet? How do we get it? It is laser cut. So we need no mask nor any etching process. Laser cut directly. And normally it is ordered with the printed wiring board, and it is also delivered with the printed wiring board. Okay, in that way, we have it all. And that's a process we use for that. And the next process is the soldering. So, soldering profile. What is important in soldering? Or what must happen in soldering? That is something, but it's some secondary. What's the primary target of when we do soldering? And okay, so it should, maybe we could say it a little more extended. It should be melted. It should wet the places or the pads that are to be connected. And it should consolidate as a good solid interconnection. Yeah. So main target. Main goal, melt, wetting, and form a meniscus. That is that nice shape of a solder joint. And if it looks nice, then it's a typical sign that the wetting has been good. And the reason is, in that case, the wetting force has been high and the surface tension of the solder has been low. That leads to a good wetting angle, small feathering angle, and in that way, it's a good sign for us. We can even see whether it has happened well. The wetting is also important. Everything that is covered with the solder should then have a metallic interconnection. So we should not have some de-wetting and so, and in order to achieve that, of course, prevention of oxidation is important, but question was for the primary target. So let's have a look at the first step here of the melting. Which temperature do we want to achieve here? Temperature in degree centigrade here is, let's say, 20. Yes. Which temperature do we want to achieve? So 800. Now imagine you have a printed wiring board. You know that green plate that is in your smartphone. And that you would like to put at 800 degrees centigrade. What do you think? 100 and? That would be too cold. So what is a let's say metallurgy gives us a hint. What is the main temperature we need to transgress when we want to melt? Yes, that value, that data was correct, but generally, what kind of metallurgical fixed point do we have to transgress when we want to melt something? It could be the eutectic point, but let's say it's more general, the melting point. Yeah, in alloys we have typically two melting points, which is the solidus and the liquidus. Yeah, so we must be above liquidus. At liquidus temperature, all is molten. Yes, at or above liquidus, all is molten. Below solidus, all is solid. There is a gap in between, and that gap in a eutectic is 0. In which other metal compositions is that gap also 0? No, just for which compositions of metals is no difference between solidus and liquidus. It's just 1 point. So we have seen it's 1 point for eutectic, and for what else is it? Sorry? It is for pure metals. Yeah, so pure metals always have 1 melting point, and eutectics. And the others always have that range. Also, the solder alloys typically are close to eutectic, but normally they are not precisely eutectic. Okay, so typically, and that's number 31, T is should be above the liquidus plus, let's say, 25 Kelvin. Okay, and in that way we have a general rule. The 25 Kelvin or degree is just to be on the safe side, yeah, because when you are just go a little, maybe there's a slight fluctuation in your oven, and in some places there was not enough time to achieve that temperature, so in some locations it would not melt, and so in order to be sure, we must go to somewhat higher temperature. So then we could say when we have a profile somewhere near the end, so SAC, the liquidus is somewhere around 220 degrees centigrade. That means we have to go to 240 or 245. So we have to go beyond that temperature. And now the question is, we have the solder paste on the solder material. Can we just go to that temperature? Is it possible or not? It is possible, of course, but what will happen when we go in too fast? Yes, so we have a limited heating, and that limited heating means, first of all, maybe it's not too slow, but at a limited rate, and that is to evaporate solvents maybe we can then go into the internet or so to look for tombstone effect. That's quite impressive. And then we maybe we go to 100 to 250, and then we increase slowly the temperature, and then we go into the, so that is for heating uniformly. And here typically we have a hot nitrogen shower, or we have infrared radiation. So there are different types of heating. Normally, when you have your kitchen oven, it's more hot air, yeah, because you have some ventilation there, and that pumps around the hot air. And so you mostly have in a kitchen stove, you have something like a hot air shower. On the other hand, you can also grill it, and that's infrared radiation, or short wavelengths or long wavelengths. Then we have a limited cooling rate. Cooling to, of course, cooling faster is making the process cheaper. Also, the production line is shorter when you cool faster, because all of your specimen is on a conveyor belt, and that belt has the same speed all through your production line. Yeah, and in that way, at least all through the oven, and in that way, we have a limited cooling rate. So typically here in the high temperature range, that is 20 seconds. And here that is, I would say, larger than 2 minutes. It depends on the product. Having bigger devices, we need more time. Okay, that's the profile. So it's important to maintain the proper profile. Nowadays, we have some equipment. For instance, it's a small instrumentation box that has several thermocouples. These thermocouples are attached to the devices on the board. And that small measurement box, typically it uses Bluetooth or something like that. And while it is running through the oven, it is measuring the profile. So during soldering, you already know what the profile is you have. Then that profile is put into a library that is assigning the temperature profile to a certain product. And in that way, a company can collect many profiles. And if a similar product comes, because that you know from the layout and from the devices that are on, you can just select a similar profile and try out if that works properly. In maybe 40 years ago or so, many thermocouples were put on the board, but they had a big bundle of cable coming out of the oven. And so at the end, we had the data acquisition and it was not wireless. And for instance, when you have a 5 meter or 6 meter long oven, you need 10 meters of cable like that thick in order to measure the profile. All of that was not so convenient, but since we have that wireless data transmission, it's quite comfortable. Okay. So we have covered all of that. Yeah. There was one open question that is also important, that was for substrate technologies. And the question was for that is question number 18. I was looking through all of the questions we had done, and I thought we had missed some. I think 18 we didn't do yet. We didn't, huh? Okay. So substrate technologies. What kind of substrates can we have? What is the method to produce it? That is important. And what are advantages? But also among advantages, I would say, what is it used for mainly? So every substrate technology has typically a certain application field, and also what would be disadvantages. So please, I'm open to your proposals. Yeah. Yeah. I called it substrate technology, but my question was not alone for the substrate material, but for a substrate, what is more important even than the base material, which is more or less the insulator base, but what is more important? That's a metallization pattern, yes? And so substrate technologies are defined by both, by the substrate material and by the let's say method in order to produce metallization and metal structure on it. So you mentioned silicon, but what kind of substrate technology would that be used for? Yes, that's good. Thin film technology. And here we could say, for instance, we have silicon, and how do we make? Then we also need insulating layers, and we need metal. What can we have on silicon? Which kind of metals? Yes, copper or aluminum. And typically we need a thin film because often we make multi-layers. And what do we need to insulate from layer to layer? Yes, so we can have silicon oxide, or we can have what is easier to handle, to take a polymer. And what's the most important polymer for thin film technology? Yes, very well. in fact, it's photoimageable polyimide. So the method is, how do we put the copper or the aluminum onto the silicon? Of course, instead of the silicon, we can also have aluminum oxide, which is a special thin film grade that makes it much more expensive than package grade. And yes, how do we put on the copper? Sorry? Raise? Brazing? Ah, no. Thin film means how many micrometers do we need? So thin film is 1 to 10 micrometers of, for instance, copper. So how can we deposit a thin layer of copper or of aluminum? Easiest way is to that can be done, but then you always need a surface, a special preparation. No, the easiest way is sputtering. Sputter, 1 to, maybe 10 micrometers is already a lot. Then what do we have to do then? Just one word. After we have one layer of aluminum or copper, how do we get it in structure? Just one word, photolithography. Then we spin on PI and photolithography. And then we can again do copper or so again. Thin film circuits, what are they used for mainly? What are the main applications? So originally, thin film technology comes from, let's say, from semiconductor technology. Here we have thin film technology, but we do not talk about semiconductors because we are assembly and packaging. So what are advantages of thin film circuits? We have thin layers, and as a result, we also have narrow layers. So we have a high packaging density. That's one thing. A small pitch, yeah. What else? As we are on special thin film substrates, the lines we have are very smooth, and very smooth lines are good for high frequencies. So thin film, one of the applications is high frequency. And very high packaging density. What is disadvantage? If something is very good, normally it is also very, yes, costs. So you do not use it for, let's say, for just low-cost applications, but you use it for high-performance applications. Also, for instance, in my lab, we have thin film technology using platinum. Then we can also use it for sensors, or we can use it. Platinum can be used for sensors at 1000 degrees centigrade. So it's thin film technology. On aluminum oxide, on silicon, it can also be on glass. And we can even make thin film technology on printed wiring boards on top. And that is so-called surface wiring technology. So what else do we have for substrate technologies? Ah, yeah, very good. Thick film. How do we make that? Yeah. So we say print and fire a paste pattern. Typically 850 degrees centigrade. There are more details we have already seen, but that's the main thing. Yeah, we print it and we fire it. Yeah, okay. Typically silver. Okay, here I repeat it, print and fire, paste at 850 degrees centigrade. And we can repeat that in order to get multi-layers. What are thick film circuits used for? Initially, thick film technology was developed because the printed wiring board technology was not very advanced. And doing very advanced printed wiring boards would be very expensive. So for a bigger board, it was chosen to use let's say a less advanced technology, and only the parts that have a high wiring density, they were used in thick film. So in the end, using thick film technology, some additional, let's say, circuit board was done on the ceramic, and that was later on attached to the printed wiring board. And the printed wiring board in that way could be smaller, significantly smaller, and it could also be cheaper because it was in a less advanced technology. With less advanced, I mean less layers and bigger pitch. Yeah. Okay, so that is high density packaging. And the second that is also important, it is high temperature. Let's say it was specifically for the range 150 to 200 degrees centigrade. Some companies even do hybrid circuits for 250. But that is very special applications. For instance, I know a French company, they're doing electronics built into the head of a drill for oil exploration. So in the head of that oil exploration, they want to know some information from the bottom of the well, and in that way they measure temperatures and vibrations and pressure and I don't know what else. And that's very important. And so they have sensor systems set down there under very harsh conditions. Costs are here for the thin film, they are really high. And here we can say costs higher than costs of printed wiring board. So thick film is significantly cheaper than thin film technology. And in that way, it is very good. Or for instance, when I was working in automotive industry, we were targeting at, for instance, engine controllers or such things for controlling injection of fuel into a motor. And here specifications went up to 200 degrees centigrade, and that could only be accomplished by thick film technology. Okay. It is higher than for printed wiring board because you can have still finer structures. But since maybe 20 years ago, this surface wiring with the laser vias on top of the printed wiring boards was introduced, the advantage of thick film technology is not so big anymore. Yeah, so no, high packaging density is very high for thin film. It is also higher, but I would say not as high as for thin film technology. Yes. Yes. So we have mentioned something. What other packaging technology can we think of? What other substrate technology? Yes, so we have LTCC. In fact, it is some kind of thick film technology. So you can say you print a thick film paste on green layers and you fire it. The rest is quite similar to thick film technology. You could also say LTCC is a derivative from thick film technology. Also, advantage here is following. You can match it to several applications. You can match to high frequency. You can match to CTE, and you can also match to power. Altogether, it's a high density technology. Disadvantage also are costs, and it is a very specialized technology. Mhm. So we are almost through. Yeah, go ahead. Which technology? It can. Yes, we could say it is suited for medium power. The reason is for high power, you need good insulation, let's say for several hundred volts at least, or even 1,000 volts. But for high power, you also what you also can have in thick film is very good insulation. Yeah, but what you cannot have with a 10 micrometer or 8 micrometer line is high currents. Yeah. Which technology do we use when we need really high currents? Now we use direct copper bonding. We have some kind of eutectic brazing of thick copper on, in most cases, alumina. And that eutectic brazing can either be done with a braze like silver copper, or we can do it with that copper oxide eutectic. And in that way, we have a very good attachment between thick copper. Thick means 0.3 millimeters or so. And that is normally used for high power or for highest powers. So I would say typically more than 100 watts. More than 100 amps. And more than 500 volts or so. What is the main disadvantage? We cannot have fine patterns or no fine pitch. Now we have forgotten one technology which covers 90% of all substrates, and that is I think I mentioned it 7 times in this lecture today. What is? Yes, of course. So here we have typically epoxy glass and copper. And here we can make multi-layers from this epoxy glass. So what we do is we produce single layers with vias. We laminate multi-layers. And we have a surface wiring, optional. So that means laser vias. On top, advantage, high density. At moderate costs. And what are the disadvantages? When we compare it to the specialized advantages to all of the other, yes, for instance, density can already be quite high. I would say we just have limitations, yeah. There are other aspects that are advantages. There's no more room here on that sheet, but printed wiring boards, it is important that here you can have the same technology for prototyping and for series production, and printed wiring board is suited for production from a single unit up to 1 million units. Yeah, so it's the same technology. There is not a significant difference also in the quality you get. And also when you go to low numbers per lot, the costs are of course higher than when you produce lots of 1 million. That is quite straightforward, but costs are also still moderate. If you make a design for such, let's say you would have a special medical instrument that is just made for one person, then I would say the cost of production as a printed wiring board, they are not really significant, but all of the engineering and the design of the circuit, and so that would take most of the effort. And then you could say maybe there's half a person year, and that means 50 to 100,000 euros you put on that single piece, of course. Yeah, and in that way, costs of printed wiring boards are limited. And another thing that is important, I talked about getting the numbers of and small and big numbers. Another thing is for prototypes, you can get the parts very fast. Yeah, you make a layout, you order it, you can have it overnight. Maybe the pattern, the stencil for printing is the limiting factor then. Yeah, maybe that can take a little longer, but the board itself, I would say that you can have really fast. Yeah, and in that way, of course, printed wiring board is something that is, you could say, a ubiquitous technology. Yeah, available to everybody at moderate costs and in due time, and that is something very good. Okay. Yeah, the limitations are with temperature. So I would not go beyond 140. Limitations are with power dissipation. It is also not, let's say, having conductors of up to, let's say, 30 to 50 micrometers is relatively easy. but having thicker conductors inside such a board, again, it's not so easy, yeah, because then you have in one layer thicker and thinner, and that's hard to accomplish. We thought there were certain limitations with respect to frequency behavior, but in the meantime, processor boards, yes, they go up to frequencies of 1 gigahertz on printed wiring board. Everybody thought some decades ago absolutely impossible, yeah. And that was mainly accomplished by better design tools, yeah. So that's also such an important fact. Everybody always talks about better materials, but epoxy has its limits. But here the main progress was achieved by design tools and by better electromagnetic design, yeah. Okay, so we are finished for today, I think. Okay, thanks for your attention.